stand here.
Okay. The
Where are
tsunami
you gonna
session
sit?
this
Oh, okay.
afternoon consists of the two major portions.
Thank you.
One of the stuff is I have to use this very carefully. One of the stuff is performance-based tsunami engineering and the tsunami bridge simulation design. Those are two major components. About the performance-based tsunami engineering, this is the one we've been working for the last couple of years, supported by Keon. Hopefully it's going to be an ongoing project. The emphasis on this is we recognize that we try to work on this methodology for critical coastal facility and lifelines. And we are also heading up to developing a methodology for the uncertainty quantifications. Tsunami bridge simulation design is we do have a DOT pooled fund project, and we are trying to develop the numerical models and systematically compare with the laboratory experiments. Okay, let me just talk about the PS tsunami program. It started probably before this, but eventually it started actively right after March 11, 2011 Tohoku tsunamis. And we have several meetings trying to find what is the optimum peer's role for this. I should say, what peer can contribute the best tsunami research, impactful to California, Oregon, and Washington coast. So that's why we talk about this during the several meetings like this. And then, basically, we try to identify the peer's niche. Okay. After these discussions, we thought it is important to find, there are several other people doing some tsunami research, like FEMA tried to develop the hazards for multiple hazards, and they did not implement tsunami yet, but we did study such kind of stuff. For thinking about all other activities, what we can do by peer is we try to find the end-to-end tsunami analysis, specifically aiming at the critical coastal lifelines and facilities, so that we can extend performance-based earthquake engineering, which is developed by peer. Those are the examples of the critical coastal facility and the lifelines. That's what we're looking for. And then this is the performance-based earthquake engineering. This triple integral shown, this is the fourth time, so I don't feel bad about this. And basically this is systematic consideration. So we're integrating entire phenomena to make I should say, physics-based assessment of the risk and damage. But the tsunami case is a little bit different from the earthquake engineering. Actually, sometimes a lot. Because for tsunami, you're going to have generation and the earthquake, and that creates the deformation of the sea bottom. And then this is very much uncertain. We really need to know the displacement of the sea bottom, rather than just the shaking intensity. So it's a very difficult thing to do. And the distribution of the displacement is also important. And then creating a propagation. And then this part is pretty much handled. But once the wave reaches to the continental shelf, we have some problem. It's very difficult to predict the run-up, shoring, the reflections. And then creating an inundation. So, and then after inundations, we need to think about the impact to the critical coastal facility and the lifelines. So let's take a look at this local damage for the Onagawa before and after. This picture is taken within, let's say, about 10, 15 hours, right after the event. So you can see some local variability in the damage because this is a study building here. This part is very much protected. That's one thing. And then if I take a look at the measure tsunami run-up height, this is one got very large number. And then I got 15 meters, and then it's 100% different. So clearly, for this, tsunami methodology has to be done with probably GIS-based things, because the location is very important. And perhaps we should do a simulation-based, or I should call it a scenario-based analysis. Has to be done for this, if you think about this kind of variabilities. Okay? And then we talk about this. This is the sort of structure for the performance-based tsunami engineering. The fault rupture, propagations, and damage, and the assessment. So, in the tsunami version of the performance-based tsunami engineering is just like this. We try to make it integral formations, rather triple integral, the double integral, but it could be a triple integral or it could be a quadruple integrals. But I think you understand the concept of these performance-based methodologies. What we're going to talk about this part A is we're going to have this developing a performance-based tsunami engineering methodology. As a test bed, we use the port Khomeini on this. So that the things we're going to talk next will be the following. After me, Dr. Honki Thio is going to talk about probabilistic tsunami estimation, followed by Professor Patrick Lynett talk about simulations, and Dr. Keon is going to talk about data explorer, and I talk about evacuations. Okay? So next is the, yeah. Number 2. Yeah. And then we're going to go with this. It's okay. Okay. You have to use this.
Okay. Well, isn't this a microphone?
This one is.
Oh, okay. Well, thank you, Harry. So I'll briefly talk a little bit about the probabilistic tsunami hazard analysis that we've developed over the last couple of years. In fact, Pierre actually has been instrumental in supporting us over the last, I think it's almost a decade, with funds, especially from Caltrans, for the development of the probabilistic tsunami hazard analysis. So in Harry's scheme, we are looking primarily at these two boxes over here, the earthquake fault ruptures and then the tsunami generation, propagation, and inundation. With our background in seismology, the probabilistic tsunami hazard analysis that we developed, the methodology that we developed, is very analogous to the seismic hazard analysis, probabilistic seismic hazard analysis. So I'm showing that here in these boxes. On the left, seismic hazard analysis, on the right, tsunami hazard. And it's really the same concept. We start off with the source models, magnitude, location, and recurrence. In the case of tsunamis, we also look at slip distribution. That's very important. Then in the next step, in seismic hazard analysis, we normally use GMPs to characterize the ground motions based on the magnitude, distance, and other parameters. Although more recently, people have been starting to use systems like CyberShape to actually use simulations. And that's actually similar then to what we are doing. We're actually using simulations, tsunami simulations, to instead of GMPs, because it's more accurate and more practical. And in seismic hazard analysis, we then integrate to a site hazard using linear methods. And the same thing we do for tsunami hazard analysis, where we integrate on offshore tsunami hazard, because in that regime, everything is nice and linear, so we can very efficiently calculate, integrate over a large number of scenarios. And then for the last step, and this will be similar a little bit to, say, the nonlinear soil analysis in the seismic hazard analysis, we actually look at the inundation. Now, inundation is a very nonlinear process, and so it's very expensive to compute, and so we like to limit ourselves to a smaller number of scenarios that we look at by just tying everything to the offshore tsunami hazard. There are other things that you can do here instead of doing detailed inundation analysis. People also use sort of empirical relationships that tie the offshore tsunami heights to the inundations using scaling relations. So it's a two-step process basically we do. First the offshore tsunami hazard, and that's in the case for the west coast of the United States, it's based on sources all around the Pacific. Currently we've only used the subduction zone sources. And if we do the integration and we look at go through all these source models and everything, then this is a typical kind of a map that you get for the offshore tsunami hazard. So shown here is the west coast of the US, California, Cascadia area, Alaska, and Hawaii. And so over here are shown the offshore tsunami wave heights for exceedance wave heights for 975 years. As you could expect, very large, that is here in Alaska, Cascadia, and also in Hawaii, because Hawaii is basically a focal point of a lot of different subduction zones around the Pacific. It's kind of a hot spot in that respect. And that's why you actually find a very significant hazard in Hawaii, because it's subject to so many different sources. Typical hazard curve, offshore tsunami hazard curve is shown here. This is for Santa Monica. I'm showing you two curves. The one that's the complete curve is actually the one, the darker one. It's blue, I believe. That one contains all the aleatory uncertainties. And as in seismic hazard analysis, we can also go through the disaggregation, source disaggregation. And this, you can see here that for an area like, I believe this is also Santa Monica, you can see that the dominant sources for that location, for that particular return period, the hazard is dominated by sources in Alaska, although there are also contributions from the Kuriles, and if you carefully a little bit from Chile and some other subduction zones. So, and the disaggregation is of course a very important element, because it can help, it can basically steer the more detailed analysis that we do when we actually want to look at the inundation. Since it's a probabilistic analysis, the inclusion of epistemic uncertainties and aleatory variability are very important. And I'm just going to illustrate this here for instance, in this case, it's for the epistemic uncertainties. This is the logic tree for the Cascadia subduction zone. It basically has a lot of different branches in terms of where the rupture, how deep the rupture extends, what the behavior is at the shallow end, scaling relationships, and also the long-term slip distribution. And there are other logic trees that we have for, say, scaling relations. Actually, no, I mentioned that already. And the aleatory variability is also important to include. And as in seismic hazard analysis, we use these relationships for magnitude. For slip distribution, this is important for tsunamis. It's not important, or it's not used really for seismic hazard analysis, at least not if you use GMVs. But in tsunami hazard analysis, it's certainly important to not just model an earthquake as a uniform slip on a rupture plane, but look at asperities. And we use a somewhat simplified approach where we divide up the fault in 3 elements, and for every magnitude there are 3 variations of the rupture, with the asperity on 1/3 and 2/3 having non-asperity. And then of course have the second and the third one where the asperity is either in the center or in this case in the north. Oops. Since we're looking at ocean waves, we also need to consider the effect of tides, and we include those. It's basically on an aleatory variability, and so we include those by convolving the offshore tsunami green functions with the tidal signal. And then finally, we also have to include modeling uncertainty. And this is kind of similar to the sigma in GMPEs. And of course, since we don't use GMPEs, we don't actually have a sigma that is inherent to the process. So we actually have to come up with our own version. And actually, so Peer has actually funded us, for instance, to develop some equivalent sigmas for these probabilistic tsunami hazard analysis. And so an example of them is shown over here, where we're looking at a very well constrained earthquake. Of course, this is Tohoku. This is probably the best constrained earthquake that we have. And we look at the modeled results and the observations, and basically construct sort of an artificial distribution functions and artificial sigma for this analysis. And we do this for different circumstances, for different grid sizes, and also we sort of differentiate between a local sigma and distant sigma, because the sigmas for, say, local for the local environment in the near field are probably going to be quite different than for the far field. Okay, so now looking at a couple of results and applications. So this method, I think up to 2012 was funded by Caltrans through Peer, and since then the CGS has taken over the funding to actually produce maps for the state of California. And so the idea is that we're going to produce state inundation maps for the entire state of California. At the same time, AECE 7, the next revision will have a chapter on tsunami loads as well, and for that they actually needed a tsunami design, sort of tsunami design maps as well. And so, killing two birds with one stroke, we developed these offshore, first of all, these offshore wave height maps for the 5 Pacific states. And then for California, we actually then went a step further, and we actually did a detailed inundation, probabilistic tsunami inundation models for selected regions. So here's an example that I'm showing. It's what you see here is the offshore wave heights for 2,500 years. So that's the ACE 7. This is for off Eureka, Humboldt Bay. These colored bars are the amplitudes, and then this sort of fence over here actually shows the dominant period of the tsunamis for that hazard. And then over here I've overlaid the actual tsunami inundation maps that we're developing for the state of California, in this case for Humboldt Bay, that are anchored. Am I? Yeah. That's big zeros. Okay, and so these are the maps that I'm showing here, and I will just show a few more of these maps. This is for the Port of LA, Port of Long Beach, and Orange County. So you can see significant inundation, 2,500 years. This is for Ventura again, and then I just wanted to. This is my last slide. Show that the work that we developed here at Peer has actually found its way already in other applications around the world. So of course we have ACE 7. It's also now the most recent issue of the Global Assessment of Risk, the tsunami part, uses the same methodology, actually the same software that we developed. Same thing for the tsunami hazard map for Indonesia, Indian Ocean tsunami hazard map, and we've also started more recently a global tsunami model, which is hopefully going to be sort of similar along the line as the GEM, except that we don't have money. But it's in its early stages, and again, that will be based on, that will be using probabilistic tsunami as a methodology. Thank you very much.
you. So what I'm going to talk about today is more on the modeling side, trying to understand modeled variability with a focus on currents, right? So one of the themes that I'm going to touch on as I go through this is that if we consider being able to model the elevations of the tsunami as relatively easy, and we have a lot of confidence on that, modeling the speeds fall on the other side of the spectrum. There's a lot of variability, both modeled and natural. It's a real good research problem because we expect there to be physical variability. And of course, when we talk about design of structures, we are most interested often in the velocities. We talk about drag loads as proportional to the velocity squared. So to do this, we need really pretty reliable estimates of the velocity, or at least we need to know how unreliable they are. So these are the types of things I'm going to talk about today. Eddies, right? Eddies are what causes us the variability in the near shore. They are turbulent structures. If you're fluid mechanicians, we know that fundamentally they're chaotic and nonlinear. We should not be able to predict them in a deterministic sense, but yet they drive our currents in many situations. They're responsible for transport, large objects, small objects. They're also responsible for forces. We'll also spend some time at the end talking about overland flow, where you have to deal with interactions of structures and buildings, irregular topography, things in the flow, and how can we get some sort of a handle on that in terms of variability. So where we fall in this talk is in this box, the intensity measure. We're also doing work now on tsunami damage, trying to connect these speed predictions to damage, but I'm not going to talk too much about that here. So just as an outline, so we're going to examine model accuracy and intermodal variability. We've done a number of many model studies so we can get a handle on how these things vary. We're going to focus on two main pieces: coastal flows, meaning areas where there's already water, and overland flows, which is areas that are dry. We're going to discriminate between areas with eddies and without eddies, and we're going to talk about how spatial averaging and model ensembles may be a solution to this problem of the chaotic nature of the velocity. We'll talk about accuracy and flow depth versus speed, and again we'll look at some statistical measures of intermodal convergence to get an idea of how we can put confidence limits on some of this variability. I'll conclude trying to resolve, or at least give you some thoughts on these two questions, and one is, are point speed measurements useful for flow characterization in light of the variability that I'm going to talk about? And can we provide an expected model uncertainty if we use a single model in a deterministic type scenario? Obviously, there are implications for load calculations. So what I'm going to start with is a community workshop that we put together where we brought in a bunch of different modelers from all the different states in the U.S., a bunch of international people, and we gave them a set of problems, 5 different problems. I'm only going to talk about one, but we gave them 5 different problems, and we told them all to run these problems. So I'm only going to talk about this one here, which is Hilo Harbor. So there's the Hilo Harbor breakwater, big island in Hawaii. This is a uniquely instrumented harbor. You have a tide gauge and you have 2 AECPs. An AECP is a bottom mountain instrument that uses acoustic signals looking up to measure what the currents are. So we have current measurements at these 2 locations with the tide gauge, so you have a fairly well-constrained field case that includes velocities. I'm not going to talk too much about how well the models did in terms of accuracy here, just because I don't have time. There are challenges here, again, with these point measurements, but these types of devices, when they're in these NOAA networks, they don't sample that frequently. They're not made to sample tsunamis. They're made to sample tidal currents. So they often only sample at 6-minute intervals. In a tsunami, the current varies over the course of minutes, so you have a lot of problems with undersampling on these instruments. So I'm not going to talk too much about accuracy. I'm going to talk about intermodal variability. What you see over here in this elevation, as it's running, it's showing you the water surface elevation. The reds are high, the blues are low. Okay, so the point to notice here is that on the scale of the harbor, there's not a whole lot of variability in the water surface elevation. The area kind of sloshes around like a bathtub, but it all changes together. That is going to be very different from the current prediction. So now this is showing you the speed, where the deepest reds are the strongest currents. And what you find here is that you have a lot more spatial variability. Things change much more quickly over small periods. And also what you see is these donut type things. These are our eddies, right? So these coherent turbulent structures that get shut off. They have a mind of their own, they float around, but they contain very strong velocities. Okay, so they're essentially carrying the hazard with them as they go, and their paths are strongly random. Small perturbations to the bathymetry, to the flow, make them have different paths. Okay, so they're fundamentally stochastic, they're random processes. Right, so what you see here is that as the flow turns around with breakwater, you have strong currents as it gets pushed through. You have a lot of water getting pushed through. There's relatively shallow area here, so you see the strongest velocities. Also, make a note of our two ADCPs right here, here, and here. And the thing I want to reiterate here is that you're using a point measurement either to calibrate a model or even in real time to figure out the hazard that exists during a tsunami. If an eddy passes through one of these, you get a very different signal. Okay, so what is the chance that an eddy passes through here? It's one of these issues that we have with point measurements. And in fact, when we went through this benchmark workshop, we found some really interesting things on the modeling side when we talk about point measurement. Interesting things like the 20-meter resolution and the 5-meter resolution results gave the same numbers, but the 10-meter resolution gave very different numbers. Okay, so it's sort of this really, really hard to reconcile model convergence where you have your high and your low resolutions agree, but the one in the middle is bad. So the reason for some of these is shown here. So you have a snapshot of what we call vertical vorticity. So it's how much the water is spinning around the vertical axis. It's the whirlpool, right? So if you look at the flow, you see the water spinning around. These colors give you an idea of how quickly they're spinning. Okay? So in a 10-meter resolution and a 5-meter resolution at the exact same time, you just happen to have an eddy at the measurement point in the 10, and you don't have an eddy in the 5. So you wind up with very different peak velocities, very different signals because of this feature, this random feature. All right, so now let's get to the inner model. So again, we had 14 models, a lot of models. Everyone contributed to this. There were models with sophisticated numerical schemes, simple numerical schemes. There were models with simple equations to solve, models with three-dimensional equations to solve. So we had a nice wide range. You can take all of these models, they're all running with the same bathymetry, they're all running with the same friction coefficient, they're all running with controlled boundary conditions. So the variability that you get is driven by the modeling itself. Okay? So what you have here is you have the intermodel mean of all those 14 results of speed. And you can see you have large speeds here on the breakwater, and there's another shoal over here. And down here, this is the interesting one. This is the intermodel standard deviation, the intermodel variability across all these models. And what you see here is that you have this huge swath of high variability between the models. And you see that these variabilities have these arcs. And what those arcs are those eddies as they get shed out and they go different directions. So what you have is you have this huge area here where the model variance is on the order of the mean predicted speed, okay, which is what you would expect with an eddy. The eddy is being shed by the mean speed, so it has the speed of the mean flow. Okay, so when you have this variance, which is order 1, it's just a characteristic of the flow. You see it in the models, you should see it in the physics as well. It's turbulent flow. Okay, so we expect this. Physically, we expect it. It shows up in the modeling. How do we reconcile it? The other thing that you notice here is that these are model standard deviations as a function of resolution from the coarsest to the finest. So the strengths of these eddies are going to be dependent on the model resolution. It's another tricky thing to do with. Let's talk about overland flow here. So we're going to focus on Sendai. Sendai is unique. It's a long, flat plain, very strong flows. You had the inland inundation here on the order of 5 kilometers, so the flow went really far inland. You're talking about flooding numerical models of many, many grid cells. Should be a tough thing for an intermodel comparison to pick up. But what you find here with the two models that we tested is that they do very well. They agree quite well in where they pick up the inundation limit. And you can see that here. So the two lines are the two different models we tested. That's how far inland the water went. And the dots are the measured run-up points. So these two models, in terms of catching this 5-kilometer inland run-up, it's doing a good job. So this is promising, right? So we have two models, again, controlled bathymetry, boundary conditions, but they're reproducing the flow elevations quite well. But let's now talk about velocity. Okay, so now we look at those same plots showing the maximum velocities from the two different models, and we start to, again, see a different picture. I'm not going to show any statistics here, but if you look at variability locally at a point, you start to see 5 to 80% variability in terms of confidence limits in the speed. Right? So again, this is tricky because our structures exist at a point. Right? So you have to handle this variability in terms of model prediction. The other thing here that I'll talk about, not too much, is that we have very, very, very limited data in terms of velocities and overland flow. We have I can't emphasize that enough. There's very, very little out there. So I can tell you there's a lot of intermodal variability, but I can't tell you anything about the bias because I don't know if they're accurate. Okay? So this is the limited data we have. Those triangles are the data points, and the squares are model results. They do well sometimes not so well. The error here is within the model variance. That's about as much as we can say. I'll skip to the end here. So the conclusions where we are right now, so we have strong intermodal convergence on local maps and speed when you have areas of no eddies. So if you're in a simple spot, you're good. Right? You're talking about model variance between 2 and 20%. Okay? No eddies, easy, good, you're set. As soon as you get into areas where you do have eddies, you now have very weak intermodal convergence on local predictions, talking about 5 to 80% in terms of variance confidence limits, 5 to 95%. You can do things like spatially average, okay? And that gets rid of this because you're averaging over the eddies, but you have to average over a distance which is about 10 times the eddy length. So if you do that, you can start to come up with statistically meaningful and convergent results in that way. So the point here is that you have to be able to identify areas of eddies, which is tough. Okay? There's a very binary difference in the speed prediction when you're in areas with eddies and without eddies. Generally speaking, if you're on land, you're in this regime with eddies. Okay? So we're getting close to quantifying this, but there's still some steps that we need to take in order to plug in numbers that can be provided into the type of analysis. For example, that 100. Okay, I'll end there. Thank you.
Now everybody sees that tsunami prediction is very difficult. Lots of variability, and then less actual data, very small amount of population, and unreliable, I'm saying that the data is very unreliable sometimes, so try to find some basic parameters to make a design. It's very formidable. That's one thing we should keep in mind. Yeah.
Okay, thanks, Harry. I'll talk about the PBT data explorer tool that we developed, and maybe give a short live demo, and then Harry's going to give an example of how he's used the tool to extract data to perform additional analysis. So in this slide that you've seen a few times now, this is falling in the intensity measured engineering demand areas. So what's the rationale behind this? The rationale is to use Peer's performance-based engineering, earthquake engineering methodology for performance-based tsunami engineering. So we wanted to develop a tool that would allow the user to quickly extract tsunami simulation data from binary time series output. The tool allows you to calculate the parameters for structural analysis, as I'll show you, and then to download the entire time series at any point, which they can then use to calculate hydrodynamic effects, which is what Harry will demonstrate a little bit later. So the initial prototype that we developed as a proof of concept was fairly simple, as you can see here, but it took tsunami simulation output and in a web-based tool allowed the user to click on or define any point and then retrieve the time series data for that point for tsunami runup, water surface elevation, flow speed, and U and V velocity vectors. But we wanted to take the tool beyond that. That was really a proof of concept. And with funding from Peer, we were able to do that. In the process, we had some considerations of what we wanted in the system. we were working with pretty large spatial temporal data sets, as many folks are. But processing speed is very important. We wanted to do this in a web-based fashion, so we needed very fast, real-time access to data. And visualization and interactivity was important. The spatial context is not just helpful, it's really essential in this case. And we wanted to give the user a spatial context where they could click and interact with the data, and also do some dynamic graphing and charting and other representations. So as I said, we wanted to do a web-based interface. Like building web-based tools, everyone has a web browser, and it's very easy to go in and just access the data in that way. You don't need special software. Because it's data are spatial temporal in nature, the GIS-based platform made a lot of sense. And the one requirement that we wanted was the ability to integrate additional tsunami simulation output data without much effort. So we built it in a modular fashion where you can essentially plug additional simulations into it. And then do on-the-fly interactive charting, determination of max values, and so on. And finally, allow the user to download the data, in this case in CSV format, which you can just open directly into Excel, of course. So for phase one of this tool, we focused on the Port Hueneme area, which others have mentioned. We obtained 5 tsunami simulation output data sets, each from a different source event. Pat generated those for us. Thanks, Pat. After testing methods of fast data extraction, because we're talking about multiple gigabytes for each data set, we want to drill in sub-second speed and pull data out. We ended up doing a conversion to sort of a generic binary format, binary interleaved by pixel, which allows us to drill in really quickly and extract data. So we wrote a C++ program that we can call from the web-based tool, and then it delivers data back to the browser. So I'm not going to go too far into the technical details because we don't have much time, but as I said, it's web-based, no special software needed. We used open source software for building all of this. And it gives a lot of sort of interactive flexibility, we think, for data exploration and visualization. And this is what it looks like, as I'll show you, if I can get this to work. There? Yeah. Okay, so this is the website, a bunch of words at the top, and we'll skip that for now. But Harry does have some information on how to log into this, so anyone who wants to go look at it can, and can read through all that. So essentially the tool allows you to select a tsunami simulation event. There's a Cascadia source, Chile, Japan, and 2 Alaska sources. Pat generated a large source for us so that we could really see the Runup data on the map. So you choose a source event, and you can punch in coordinates directly if you know what they are, or you can just go click on the map. And let me zoom this out to what you see when you first arrive here. The map is constrained to the spatial domain of the simulation that was run. So you can zoom in, find a place of interest on the map, and click a point. Sorry, I'm doing this with my finger here. Click any point on the map, and it's a little hard to see on the screen, I think, but this chart, which is inundation depth, is being updated on the fly. What you're essentially seeing on the map here is a representation of space-time data cube, right? So we have 3,600 time steps in here, so for any point that you click on the map, you're pulling out a time series of 3,600 points. That's what's being charted along here. And if I collapse this down, it's like these are all expanded, but there are actually 6 charts down here, and you notice that each one of them displays a max value. So anytime you click on the map, that max value gets updated, and all of the charts get updated. So we're showing multiple different parameters here, all being calculated on the fly. The map itself allows you to load in other data layers, any of the Google-based layers, but also we have the bathymetry layer on here as well. And there's a bathy topo layer behind the scenes that's grabbing the elevation for every map click. And we also have the max flood surface elevation, which can be plotted as a grid
me show you some kind of application for this tool. How do I do it? What was it trying here? Let's see, this is GIS based, and I think this is important to do this because tsunami effect is quite a bit different from place to place. But the real eye-opening example was what Pat showed to us about the giant formation. So we really need to know where it is. Okay, my example is I just take a look at this simple, rectangular shaped buildings. And then I pick up the 1, 2, 3, 4, 5, 6, 7, 8, 9 points, each points. It's about 5 meters apart. And then quickly take the data out and then calculate the velocity and inundation forces. So that's the sort of a list I can get immediately on that. And then I can also put up, this is the inundation, such a close area, and the variability is remarkable. But at the same time, good part of this is I can at least, right or wrong is different story, but at least I can quantify the errors. Okay, this is for the flow speeds. And then if you know flow speed and the inundation depth in time series, then I can calculate the forces. This is the linear momentum flux forces, assuming that this force to be flow to be a steady state. And then after this, I can get some error estimate for this, 90% confidence interval for this. This is just one example. And the one thing why we need to do those time series data is the following. When we try to make an analysis for tsunamis for critical facility and the lifelines, we just need to be very careful, right? Like for Japan case, some of the concrete building is toppled. One of the major mechanism for that is the buoyancy force. The buoyancy force reacts with time lag. It does not respond with the raising water. So we need to know the time series of the inundation depth. And another thing we need to know for the time series data is, of course, try to find the soil liquefactions. Momentary soil liquefaction is caused by I think that the eroding from the soil surface by the inundation up and down. You have to know those time series data because soil response is based upon the diffusion equations. So if you really try to find those kind of stuff for the critical structures, we have to have time series data. Okay, so for the summary and remark for that here is, as you see, the response is so quick. Huge amount of databases in here. And then you can retrieve the data very, very quickly and very convenient way. And this portal is very user-friendly also. So that's the advantage of this. So once you get those kind of data, we can get the hydrodynamics force. And that allows us to examine spatial temporal data analysis. That's the thing we can do. And at the same time, we can get to quantify those uncertainties on this. So very fast is one word. Another thing is, this is really give you a very nice probabilistic analysis. And right now, the data we have for this portal is only 5 or 6 cases. We'd like to expand to the 25 or more cases for this tool. And then using this platform to do exercise to find that the quantification of the uncertainties. As you can see, if you have this kind of IT tools, you can sort of combine, or you can attract different discipline people working together on this portal. And then you can, at the same time, you can actually quantify for the model data. Let's see, this is my last slide. All right. This is my last. Okay, that's my last slide. And then I can very quickly talk about the casualty. And after that, I think I have to give it to I have been working on the tsunami hazard and casualty estimate. Because casualty is very important things for the tsunamis. Okay, tsunami is very rare event, and but you know that hazard kills the people. So this is sort of a effects of this performance-based tsunami engineering part. Okay, whenever you try to make a casualty estimate, people talking about the agent-based model. And that is fine, it's very nice exercise to do this. This agent-based model, we tried to do that, I tried to do that about 10 years ago. And this involves significant uncertainties in the human behavior. Human behavior is totally, question marks. It's very difficult to predict. So, whenever you do the agent-based modeling, you can get the results, but we have to know there creates significant amount of uncertainties. I'll show you why I'm saying this. This is the statistical data for the maximum tsunami height versus fatality rate. Okay, this is a log plot. This is a linear plot. Okay, I extract several cases. This is for 2004 Indian Ocean's case and the 2004 Thailand, 2004 India case. They have some trend to increase, some correlations. And this is for the 1993 Oshiri case and other case, some kind of trend. However, if you take a look at the Japanese case, there's no trend at all. So, only trend we can get those statistical data is, that the tsunami fatality rate diminishes when maximum tsunami height is less than 1.5 meter, nothing else. Unless you're talking about the one given event for a given locations. So conclusion for this analysis is we have a very weak trend for the fatality rate. Fatality rate increases with the tsunami height for given events and the given localities. So once you have those data, you cannot translate to predict other locations or other events. More likely, people's prior knowledge is more important. The education is more important. So how the society reacts is more important than the tsunami's actual physical forces. So that's the thing. So important factor for the tsunami casualty estimation is time. Time related. Time is essential for the estimating of tsunami casualties. I think I don't have so much time, so I just talk about what's next. And then we can discuss this one tomorrow. We have a discussion session tomorrow. What's next? Okay, phase 2 project, that's what we're looking for. In the phase 2, we're going to follow through and complete this TBT methodology, we just explained to you today. And then, first things we'd like to do is incorporate additional cases all the way up to 25 progress data sets. So that gives you an arena to analyze the quantification of the uncertainties based upon some physics and mathematical-based models. So if you have sufficient number of the hazard scenario, which is important to develop the mathematical-based algorithm to quantification of uncertainties, I just mentioned that. For example, that's a Bayesian-based data simulations. If we're talking about a casualty estimate or something like this, this might be the one thing we can think about this. And if we have lots of data and this kind of tool, at least this kind of tool can encourage the people to develop those algorithms. And then we're going to have a developed algorithm to uncertain quantification to be incorporated to this platform for use. And then after this, we'd like to take this one to a design specifically for the assessing, for the design making processes. I think that's what we're looking for the phase 2. And I think this is my last slide, and I think part A time is totally used, so I have to give it to the part B talk, but I'd like you to remember for this presentations And we have lots of time to make a discussions tomorrow. Okay? So, happy to be a Professor Michael Scott's going to lead for this.
Thank you, Harry. So I'm leading session, or part B of this session. And so part A was kind of focusing on the kind of the source to site propagation and kind of what's height and velocity of flow at a point, and how a point being a structure, right? And what kind of, part B, what kind of tools and what kind of analyses can we do with that information for critical structures such as bridges, which Pat will talk about. And then I'll talk about some other simulation tools we use with bridges, and Mike Motley will talk about some advanced modeling of tsunami effects on bridges. But this is kind of getting back to the end-to-end simulation. We started with the source, now we're getting to the site and what Pier's been doing, some recent and current efforts around bridge analysis for tsunami loading. So Pat.
So what I'm going to do here is give kind of a brief overview of this project. So this project is relatively young. We haven't made enough progress to really talk about some of the detailed things that we've done so far, but we will in the coming meetings. So the purpose here is to develop tsunami guidelines. Just some images here, a couple images in the middle here from Japan, and an image below from Indonesia in 2004. So our goal here is to develop tsunami design specs. So the project is to come up with the development of some sort of guidelines, right? So for the estimation of loads due to tsunami. Most of the work will go into the development of those guidelines. It covers a wide range of things, from estimating the hazard appropriately for bridges to developing a loading calculations and developing a guideline. One of the final steps will be to include a verification of these guidelines for a set of existing bridges to see how well it does. So the project right now is supported through a pooled fund, the state pooled fund through different departments of transportation of all the Pacific states. Our states here, which have many coastal bridges, all subject to the potential of large tsunamis. So the representation is really specific. So we have 5 major working groups. Working groups 1, 2, and 5 are going to be the main ones, but we have 5 major points. So these also kind of lead in time where the work will go. So the first working group is tsunami hazard and mapping. So coming up with the hazard indices responsible to drive the loading calculation. So this group is led by Hung Ki and myself. I'll say mostly Hung Ki, but with a wide group of people. The idea for this project was to have a few centralized people running each working group to do most of the work, and then to bring in larger groups from the community to run workshops and have community discussions to make sure that we had a wider range of inputs, so that we were doing things not in a bubble. The second working group is to come up with sort of the meat tsunami loading of bridges, and so that's led by Michael Scott, again with a range of people to add input. We include groups on bridge detailing and geotechnical issues. Those are relatively minor in terms of the entire scope. Minor only because we were judging where to put our resources in terms of funding and what to focus on. The last working group 5, is led by Tom Murphy, and this is the code. This is the actual writing, the discussion of the prescriptive method. So again, here I'm just going to focus on those 3 groups to tell you what we plan on doing, what our deliverables will be, what you expect to see in the coming years. So working group 1 has 3 major components. First is the development of a tsunami hazard map database appropriate for the design of bridges. So right now we're looking at what all of the states are doing, and they tend to do things differently and not necessarily consistently, so you have to find some way to bring all of these together. The specification of the hazard level here for bridges is going to be at the 1,000-year level. So that's going to be consistent with other hazards that are looked at for bridges. It has a disadvantage in that you can't directly use some of the AAC7 maps because there are different hazard levels, but you can use similar approaches. We'll include quantification of uncertainties in a way appropriate for bridges, and so this will lean on some of the work that we talked about in Part A here. The last component here is the specification of the site-specific hydrodynamic information. So there are lots of ways to do it. You can run numerical models. You can do simple things. Right now in AAC7, there's something called the energy grade line method, which is best way to describe it. It's somewhere in the space between a robust numerical model and a prescriptive method. It tries to include some physics in a very approximate way. We'll look at other options, including transect-based models or some other way to include variability from this modeling tool. Second working group, again, this is Michael Scott, so he's going to talk a little bit more about this and some of the work that's going to lead into it later. First major task is the literature review. This is where we are right now. Identify knowledge gaps. Okay, so what do we need to fill in order to bring all this together and come up with loading approaches and loading counts for bridges? Workshops involved here, lots of discussion. This part will lead to a testing phase, right? So we have knowledge gaps. We have to find some way to fill those knowledge gaps. This testing phase is likely to focus on numerical simulation only because the budget allows a lot more numerical simulation than it does physical model testing. And the tools that we'll use in this phase will really leverage some of the work that has happened at the bridge simulation workshop. After all this, the loading calculation approach, and that leads you to the last working group, Group 5, again led by Tom Murphy. 2 phases, a draft, lots of discussion, and a final. This whole project is 3 years in duration, and it's expected that this final guide spec is going to be done sometime in June 2018. So it's forward-looking, we're looking down the road. We'll get there. These are our sponsors. If you have any questions about this, you want to be involved in this, you want to learn about a little bit more about what's going on, feel free to come talk to me, talk to Yusuf, talk to Steve, and we're happy to share more information about what's going on. Okay. Thank you.
So Pat discussed a current project that Pier's involved with around bridge forces and determining loads on bridges. And I wanted to talk about a recent effort that Pier supported on a workshop held in December of 2014 at Oregon State University around simulation. Okay, so that'll be the subject of this talk, and then Mike Motley will talk about some more advanced simulation details. Okay, so as has already been established, wave loading on structures is important. All right, given recent natural disasters, it's become a very important topic of study, and determining if our critical structures are resistant or can resist such forces observed in these recent natural disasters. Happy thumbs here, sorry. Okay, so simulation is important. Well, I'm using important way too much. But simulation of bridges, evacuation shelters, and power plants, and other critical facilities is essential in order to develop a performance-based tsunami engineering framework, which is one of Pier's thrusts. Okay? And also considering the case of tsunamis following earthquakes. Simulation will be a big part of that effort. Okay. So, just like with earthquake engineering and modeling the response of structures to seismic forces, a lot of the same questions come up when modeling the response of structures to hydrodynamic or tsunami type loads. How accurate do models need to be? what's the right balance between accuracy and efficiency? You know, can we get away with 2D models? Or do we give up too much accuracy for that efficiency, or do we have to go for 3D models and then other tweaks within 3D models? You know, what's the right balance? Right? It's not necessarily the same answers, same questions, but different answers, I believe, between earthquake and tsunami type simulations. Okay. But just like with seismic simulations, boundary conditions and model parameters play a big role in the response, as does characterizing the hazard accurately. All right, so flow height and velocity are really the two things that characterize the hazard in terms of figuring out the loads applied to structures in a tsunami. Okay. And of course, can refined analyses inform the estimation of loads in order to determine design specs, like Pat just talked about. Okay. So to this end, back in December 2014, peer funded or supported a tsunami bridge modeling workshop. There's about 33 participants from the US and Japan. About 1/4 were from Japan. Of the 33 folks in attendance, a lot of the faces you see here are probably in the same room or were at some point throughout today. Okay? But we brought everyone together to compare simulation methods and discuss differences in results, kind of identify knowledge gaps, and see where we need to go in order to inform or to drive peers' efforts around PBT. Okay? So these are the participants. There's a web page there where all the workshop materials are made available, and essentially it was a blind prediction contest or quasi-blind prediction contest of experiments conducted at PWRI in Japan, I believe in 2012 or late 2011. It was after the Tohoku event. But what we see here is a 30-meter long wave flume. Pointer here. So it's a flume. There's a reservoir of water here held back by a gate. All right, so you can see the water level. It's pretty high here. There's a standing water level. Down here is a 1 to 20 scale bridge deck model stuck in the flume. You know, some 10 meters down from the gate. The total distance here is 30 meters. Okay. So this gate is released. All right, and then a tsunami bore ensues and impacts the bridge superstructure. And then this is well instrumented. Pressures are taken all over the deck at different points. From those pressures, you can determine forces and look at the response or look at the superstructure response to the tsunami attack. Okay, and so just again, the gate's released, and then the tsunami just goes down the phone. Okay. There are a lot of different cases where a lot of different experiments were run by PWRI, but only 4 of them were chosen for the workshop. Okay. And there were 3 different deck types. So there was a type A, a slab bridge configuration here, restrained at 2 points. Okay. And then a 4-girder deck bridge, all right, restrained, down here where the vent caps would be. And then the same deck type C with a protective bumper on the side of tsunami attack, right? To kind of design to dissipate the tsunami flow and there hopefully reduce the forces. Okay, and then so the 3 decks, 4 different cases. It's probably a little bit hard to see here, but there were differences in the computed wave height that based on some calculations, what the wave height would be at the point of contact, as well as differences in the still water depth. All right, so there's this water level was varied, as was the level in the tank, and based on relationships between those two and the flow, you could predict what the wave height would be. And the wave height and velocity was measured by wave gauges about 1 meter in front of the deck. Okay, so differing wave heights, differing still water depths, 3 deck types, 4 cases. There was about 8 or 9 different software packages that were used, employing a wide variety of formulations. All right. So I don't expect you could read all this table, but the key things were that there were volume of fluid approaches as well as finite element approaches. Okay, so one of the finite element approaches was based on open seas using the particle finite element method. A volume of fluid approach was based on open foam, which Mike Motley will talk about here in a few minutes. And there were various others, LS Dyna, the NPM method by Pedro Arduino at University of Washington, some of the methods. Okay, so there were 2D and 3D models, single and two-phase models. So single phase model is just the fluid. Two-phase is where you model fluid and air, right? Because air pockets end up being a pretty big deal when they get trapped under the decks, as again Mike will talk about here in a minute. Okay? As well as turbulence models, how you represent the high velocity, highly chaotic flow around the structure, right? at the time of impact. Right? Okay, so this doesn't show up very well, does it? But at any rate, I'm not going to kill you by data results here, but what I wanted to show here is the blue dots here, the dark lines here, are the experimental results. This is for the total horizontal force applied to the bridge deck for case 2. All right, one of the 4 cases that was examined in the workshop. Okay. The experimental result, the numerical results. Some of the peaks, the impact force or the surge force is right here. All right, some are down here. The experiment's about right here. All right, so a lot of variability in the peak, and then even some variability in the steady state flow. You know, once we just have the bridge overtopping or flow overtopping the bridge. Okay, some are stable, some are kind of oscillating. All right, so there's a lot of variability in the numerical results among the different softwares. Same with the vertical force, the total vertical force. So, the flow is going to cause horizontal force as well as up and down vertical force, depending on the flow. Okay, and that's some different effects there. Okay, but again, a lot of variability. All right. Not unlike earthquake engineering simulation. I helped write open seas. I know there's a lot of variability in models. Okay. No chuckles? Okay. All right, so last slide here. The key observations from the workshop, the takeaways were that it is worth doing 3D models when you want to look at the hydrodynamic forces on structures. Okay, so the 2D models we found in the workshop just didn't do very well. All right? And that was due to localized air pockets and vortex shedding not being accurately captured by the 2D models. Okay? The 3D models also help you look at the effects of skewed bridges and other sloping and things you just can't model in 2D. Okay? Turbulence models tended to improve the results compared to the experiments, and of course the initial and boundary conditions were all important, especially with respect to how that gate opened for the water tank. And so there's additional details on the workshop webpage and the final report, which is forthcoming. Okay? And at this time, Mike Motley's going to come up and talk about some of the more detailed modeling within open foam around modeling tsunami forces on coastal structures. And then we should have time for questions for parts A and B at the end of this talk.
Okay, thanks. So yeah, I'll talk a little bit, kind of building on what we've been talking about for the last 5 or 6 presenters, and show some of the effects, the 3D effects that Michael was talking about with a couple of case studies and some of the things that we can miss when we're only doing these 2D models or doing the simplified models. I left one co-contributor off, Mark Eberhard, who's been working on this project as well, and so I just did want to acknowledge that. So we've been doing CFD modeling at a couple levels. We've talked site to source, then we talked about structural components doing that. So I've been doing some models with both community scale, structural scale, trying to see where we can bridge those gaps. The physics becomes quite different when you're talking about generation versus what's happening to a structural component. And so we're trying to figure out ways to do that. Today I'm going to focus more on the structural scale force prediction models for a couple of bridges that we've been looking at recently. And so the model that I've been using is open foam, open field operation and manipulation. People have been using it for a wide variety of problems in computational fluid dynamics. It's got a complete package with about 80 solvers, 170 plus utilities. It's constantly being added to. They just released it in the last few months, the latest edition, version 3.0. My students have been very happy with it going faster, which is a big deal for CFD models. It's got mesh generation and refinement capabilities, which I'll show quickly how we do that. We can convert CAD geometries, simple or complex, to develop our meshes. Parallelization, which becomes very important for these fluid problems. We usually run our models on about 64 processors. We've been happy that's enough. We've taken it up higher. We've taken it as much as over 500, and it scales to over 1,000. The other word that's not on here is free. Okay, and so that's a big deal for a lot of us. And with an open source code, we're able to not worry about licensing issues when we have to deal with really ramping up the parallelization. And then this will be available on the new Near-East cyber infrastructure in the coming months. I know Pedro Arduino is going to be talking some about that tomorrow, but we were at the workshop a couple of weeks ago, and they're happy to get that on there and happy to let people use their supercomputing capabilities to keep this, or to let people start practicing with this. And so, just quickly, in terms of meshing, building your model, we've got capabilities. We can build a bridge. Here we've included the whole 3D bridge with the substructure as well. We import it into open foam, and then we mesh around that. And so we end up with a kind of an empty block that we insert the bridge into. It does its best to snap squares around the bridge, and then refines all those edges so that we get a nice curved shape. So from that, these are the open foam results from Michael's plot with all the different analyses, looking at 2D versus 3D. For some reason, black lines don't show up well on this screen, but the 2D plot is a little bit worse than the 3D for both the horizontal and the vertical force. If we look here, we can see that we're overestimating the peak much more here for the vertical force. It's the same down here we see a slight overestimation, the horizontal force for the 2D, a little bit more than the 3D. The results aren't that different. And that's mostly because the flume model of the bridge is essentially a 2D problem. Okay, we're picking up little things, little improvements. We model the gaps in the edges to let the air come out, which we'll see is, I believe, causing these peaks. Getting the substructure in there, just modeling the actual physical domain that was experimented on. But what we can start looking at is, let's take that bridge that we just hit with a wave and start rotating it. Okay, what happens when we skew it? What happens if we slope it? How does that change the results? And so what we find is that, these dotted lines. So we introduce both horizontal force and uplift force for what we'll call a 0-degree model, no skew, okay, which is equivalent almost to our 2D model, right? And we do introduce overturning moment. But when we start to skew the bridge, what we find is that we start to introduce horizontal forces in the what we'll call the z direction, and then we introduce both spinning moments and what we'll call pitching moments where the bridge wants to turn over itself in the direction that we're driving. I know that some tests were done in the OSU Flume recently on skewed bridges. I hope that when we see those results tomorrow, they look something like this. We were kind of doing it numerically, but the fact of the matter is it starts to introduce some things that you wouldn't necessarily be able to capture with just a 2D model. Okay, if we think about what happens if we slope the bridge, right? We have to ask ourselves, if you're going to do a 2D model, where is the slice, right? So with a sloped bridge, if you slice it in any specific spot, its distance to the water surface is going to be higher or lower. And so what we find is we do start to see changes in the uplift force, in the horizontal forces, and introduction of spinning moments based on when the water is hitting just one side of the deck. And so these are the kinds of things that we would miss in a 2D model. We can try to start extrapolating it in, but the 3D models are able to capture that a little bit better. Another thing that was brought up was fluid-air structure interaction. Okay, we said that we had those peaks which may be occurring in the 2D model and not in the 3D model, and maybe because of air. So we started modeling this bridge. It's a bridge in Washington. It's not in a tsunami zone, but we at least wanted to start modeling a bridge that looked more like a bridge and less like an experiment. And so if we model, this is the total horizontal force on the bridge. When I say total force, sum of all the pressures on the entire, every face of that bridge we showed right here, steel girder bridge, and we see these total horizontal forces. Now what happens if we break this up into the components? So this is each individual face from the cross section. And so we're doing 2D here. What we see is these equal and opposite curves that start to propagate across, okay? And so they're not necessarily contributing to the total force, but they're showing up as big peaks. And so we were curious as to what was happening. And what we find is that the red curve here and the green curve correspond to the back face of the front girder and the front face of girder 2. All right, equal and opposite, it's on these two faces. So we can assume this is air. And so we see that this continues to follow along, corresponds to all of our peaks, okay, all the way through. We see these little pulses of the air getting trapped underneath the structure. And in the horizontal load predictions, it doesn't end up causing that much of a problem because they become equal and opposite. They don't contribute really to the total load, okay? Okay, but for the vertical, right, there's no equal and opposite. Okay, so we end up with these peaks. Right? And so we're looking at that and we're trying to say, okay, the water's going up under, we're getting these big uplift peaks. But when we start looking and matching these peaks with the air pressure peaks that we're assuming from the horizontal load, we're finding these peaks all coincide with air pulses. So we're not seeing the water come in underneath the bridge to cause big loads. We're seeing these air peaks. And if you go through, calculate your surface area, do the math matches up with these peaks. And so with the 2D model, maybe we're seeing air entrapment that will be there physically, but maybe we wouldn't. And so we're running 3D models right now to see if we can eliminate these peaks just by putting gaps in on the edge and seeing whether this is real or numerical. And I think the answer will be somewhere in between. And so lastly, what I'll talk about is, here's a bridge that we've been modeling. This is an open seas model, or sort of an open seas schematic of the bridge that we showed a few slides before. What we're trying to do is say, what happens if we build a structure, run open seas, subject it to an earthquake, and then subject it to a tsunami? Because ultimately, that's what we're all trying to do, right? We see these integrals. We want to. This is extending the integral that we keep putting up here. Okay. So here's an open seas model of that bridge. I've never used open seas, so I'm not going to pretend to know exactly what they're doing here. But we have a PhD student I'm working with, Lynett, trying to do some of this and couple it. And so then we build a CFD model. So this is our CAD drawing of that bridge. We've got every span, every detail. If we look at our mesh, we're modeling exactly what we would expect to see out there. We run a wave into it. We get a dynamic loading profile, and we can attach that to the loading of the bridge after the earthquake. And so hopefully we can see this top left plot will be displacement of one of the columns versus time. The bottom left will be the shear force in the column versus displacement. And then we'll see how the bridge reacts to an earthquake and then the tsunami. The displacements are magnified by about 100 times, but just to see the scope of what the tsunami does versus what the... So here is how it's displacing from the earthquake. And we see this behavior, this cyclic behavior going back and forth. The subsequent tsunami comes in and hits it. Extensive loading takes the whole thing out. And so these, I get asked, how do these loads compare with seismic loads? They are big. It's not something we can just expect that we will be meeting all of our demands inside of the design. And so we're still working on that. This result was provided to me at 4:30 yesterday afternoon, so we haven't had a ton of time to dive into it. But what it does say is it leads to the question, right? We're talking about our 2D versus our 3D models. What's accurate, what's not, right? One of the big assumptions that we make when we're doing our fluid modeling is that our structure acts with small displacements, and we put it in as rigid boundaries. And as I look at that, that's anything but a small displacement. And so extending this, using the models, but then it comes down to understanding what we can do, what each model is capable of physically, and exploiting that. But computationally, we can start doing some of these 3D models. The time frame for something like this is on the order of days to weeks, but a number of years ago, it was on the order of we just won't do it. So with that, yeah, I think that's all I have. I have a 5 on there instead of a 0. So.
So I think we do have about 10 minutes for questions. We kind of skipped the question portion for part A, so if Harry wants to come up and help moderate questions, we can take any questions related to the presentation for part A or part B, anything you've seen in the last 81 minutes. Yes, question?
One of the lessons from the Kobe earthquake, the Japanese bridges that collapsed, was that they evidently put all their eggs in the strength design, but they had no fuses. It seems like a bridge deck philosophy might be to design in fuses so that the foundation and everything but the deck remained intact. Then all you had to do is replace the deck. There's a lot of composite materials and stuff that might make that rapid. But what is the optimum material for a bridge? There's also the issue of, you might be hit by a ship or a shipping container or all these other things that and wouldn't you want to know what the maximum loads could be and not what your probabilities are? But should there be fuses? This philosophy...
Well, you stuck in quite a question there. What's the optimum material for a bridge deck?
Well, when do you want to build the bridge? We have this...
That's like the $64,000 question. Right? So everyone try to answer that one. But so debris. So yeah, debris is something that I know with the material point method, which we briefly mentioned from the workshop, but that's something that Pedro Arduino has been modeling a lot of debris impact with the material point method, and it is a big deal. And I believe Ian Robertson, who's here, has done some experiments with debris on structures in a tsunami load. So, I mean, those things are being looked at. We didn't talk about them today here, but it might be a subject in the session tomorrow where we go more into detail and have a little more discussion on things like debris and damming effects, with not just large shipping containers, but also just 2x4s and things that get caught in the flow and kind of well up at one point on the bridge and add mass and have more loading on the structure. We'll probably touch on it some more tomorrow.
Quickly, I think one part of the question was, should we use, should it be a fuse? Should something just break away? For buildings, I think that's where people are leaning, right? It's surface area. We want to eliminate surface area, but for bridges, we don't want to eliminate the bridges. We don't want to just let them wash away and have things there, because as soon as the event's over, these are our lifelines, right? So it's sort of a different design philosophy from thinking about bridges, where you absolutely don't want to just have these failure points and let it wash away.
I'll confirm that I will talk a little about debris impact tomorrow, but it wasn't my research. So.
You were involved, right?
Yeah. But I had a question. The bridge uplift and trapped air. I want to caution against you always allowing gaps at the end of the bridge. If we do that in our models in the lab, that might be a mistake. Concrete bridges typically have bulkheads, bridging elements that close off, and that area is indeed trapped.
No, that wasn't to imply that we would never have a trapped air. It was more the differences that you would see in certain areas, right? Or certain scenarios. Physically, we may find that in trapped air, but modeling in 3D, I would expect is going to give a better estimate of the actual extent of the trapped air.
Time for maybe one more question if it's out there. Okay, thank you to all the speakers. Thank you for your attention, and I believe Grace, we have where's Grace? 15 minutes. 3:15. We'll resume at 3:15, about 20 minutes from now.